Hello again. So here is part 2 of all the examples I prepared for you for chapter 24. We're going to continue now with a problem from section 24.4, which is part of the dispersion and visible spectrum. So the question here is, by what percent the speed of the blue light is less than the speed of the red light? So essentially, because they ask you this question and it's worded this way, the red light will be your standard that you have to calculate by what percentage the other one is less. In this case, they already know it's less. And they ask you in a specific film or a specific glass, which is silicate flint glass. And the graph is given. You have the index of refraction on the y-axis, and you have the wavelength. So what I did, I actually draw what they ask us. Say 450. 450 is in the blue range spectrum. So if you go with 450 and intersect the graph, and you count the units here, it's about 1.64 for the refractive index. So from the graph, we get the refractive index for blue about 1.64, as opposed to for the red light, it's about 680. It's about 1.615 or 61 or just 1.61, and so I wrote it there. For the red, you get that. Now, in order to calculate the percentage difference, and you need to have the velocities of the light through this particular material. So now the only thing that we have given is the refractive index. But you know by the definition of the refractive index, that is speed of light divided by the velocity through that material. We're going to pull out velocity from here, right? So that's C over N, meaning that the percent of difference now is V blue minus VR, which is V red, over V red. Replacing the velocity with C over N for each respective of the colors. You can factor out C, or you simply simplify it out. Plug in the numbers that we got from the graph, and you calculate it, and all of a sudden you get a negative number. So the question is, hey, what does that mean? That means that the light speed is slowing down. By how much? By about 1.5%. So I wrote it in words here for you guys, so meaning that the speed of the blue light is slower than the speed of the red light. And that's kind of interesting, because you can see that that's inverse proportional with the index of refraction. So that should be to be expected. I would get worried if you get a positive number, then something happened in your calculator. Alright? Very good. The next example we have here is from the next section, which is the single slit diffraction. This is your section 24.5. Let's see what they ask you here. Monochromatic light falls on a slit. Here's the opening of the slit. That is 2.6 times 10 to the minus 3 millimeter wide. So that big D is that number. If the angle between the first dark fringes on either side, so be careful what they tell you. This conducts, so you draw your central line, and then you know you have a central maximum, and here's your minimum. So now you can actually look. They tell you between two dark fringes on either side of the maximum. So they give you this total angle is 28 degrees. What is the wavelength of the light used? So from the picture that I draw, you see that the angle theta, or 2 theta, gives you a 28, meaning that makes theta easy to find, 14 degrees. Now, we are talking again about interference here. So what's happening here? It's actually a diffraction. So the equation given here, it's d sine of theta equals m lambda. Very similar to before, but this is a one single slit, so it behaves a little bit different, okay? So this tells you where all the minimums are for the diffraction pattern that's formed in a single slit. So because we are talking about the first dark fringe, then you only have to look at m equals plus minus 1 on each side of your 0. Meaning that if you pull out lambda from here, you get d sine of theta, and then you make m equals 1. That's an easy way to conduct this. You plug in your numbers. Be careful to make sure you convert. This was 2.6 times 10 to the minus 3 given, but also times 10 to the minus 3 because it was in millimeters. This is converted into meters, sine of 14, and you get this number. If you really want to be kosher about it, hey, you can convert this into nanometers. So if you multiply this with 100 and divide this by 100, right? So here you go, you didn't change anything. Then 10 to the minus 7 divided by 100 is 10 to the minus 9. That forms your nanometers right here. So 629 nanometers. Next problem is problem 6 in your packet right there. This is in your sections 24.6, 24.7. They talk about diffraction gratings, which is nothing else but a single slit made over a certain distance. So in this problem, they tell you that you are having a diffraction grating that is 7,800 slits per centimeter. So I was trying to kind of make it here, and the only picture I'm getting is the distance between two consecutive ones. So I'm just kind of zooming into that. And then you have white light going through there. So this white light, when it goes through a diffraction grating, you know, it separates the light through the whole spectrum. So when they talk about, 410 nanometers, they're talking about blue light. When they're talking about 750 nanometers, they're talking about red light. But they ask you, how white is the first order of spectrum? In other words, you can make two drawings, each one representing either the blue light and the red light, and then you overlap them, and you get something like this. Okay, so essentially when they tell you how wide it is, that means, hey, what is the distance difference between the central maxima to the red light minus the central maxima to the blue light? So XR minus XB. We don't know much about this problem, do we? So they tell you that the screen is 3.4 meters away, so that's that L. You know that distance D, and that's probably the key here. That distance D tells you that in 1 centimeters you have 7,800 slits, meaning you can calculate D by converting your centimeters, 10 to the minus 2 divided by 7,800. There you go, you're going to have D. So in order to use the formula d sine of theta equals m lambda, and you're looking at the first order, right, because they want the first order, pulling out sine of theta from here, it's m lambda over d. M is going to be 1 later on, but getting theta by itself, it's inverse sinus of this quantity. Knowing that m is 1, and knowing that d is 10 to the minus 2 over 7,800, you're going to plug in that information here, simplify correctly, and you get 18.651. So I plugged in 410 nanometers, hence that's the blue color right there. So theta blue is about 18. So if you really look here, you expect the blue light to be smaller. If you happen to draw this incorrectly, by the time you do the calculations, when you plug in your numbers, you will get the angles correctly. So they will actually tell you what the angle is, and you will be able to depict which one is which. Okay, theta red, same idea. You plug in your 750 and you get an angle of 35. Good, same approximation like before. Tangent is equal to sinus. However, in this case, they only ask you to find x. So tangent of theta b in a big triangle, right? If you look on each one of those triangles, there's your x, so opposite, and here's your adjacent. Follow the story right here. So xb will be L tangent of theta. Similarly, L tangent of theta for the red one. Plug in your numbers. And for the blue light, you get about 1.14. For the red light, you get about 2.45. So that kind of matches the opening of your angle. So your delta x, or how wide that is, you subtract the two numbers and you get 1.3, about 1.3 meters. So that's it for this part.